I was postdoc at Bar-Ilan with Yehuda for 1 year, 3 years ago, I think, for 1 year, and it was really a great experience, both from a scientific point of view and also from a personal point of view. So it's really, really a pleasure to be back here, and it's always nice to be back. So I found a few typos in the slides that you that were printed, and I'll try to point them out. So the first typo is in the first slide. So I'm going to talk about this paper that it's called A New Approach to Practical Active Secure Multiparty Computation. And clearly this is not new anymore because this paper is 4 years old, so this is not a new approach anymore. And the code name of this is TinyOT. This was actually just the name of the SVN on which we were doing this project, which at some point leaked and got popular. So so this is also forgot to put in the slide. This is This is based mostly on joint work with Jesper Nielsen and Peter Noddahl, who is in the room, and Sai Burra. So I couldn't make things easy, so we have 3 hours, but 2 sessions and 3 parts. So in the first part, I'm going to tell you something about secure computation with a trusted dealer. So this is something that I think everyone should know. So this is not specific to this TinyOT protocol. This is an approach to secure computation which is now getting more and more popular, and I think this is really something that everyone should know. So please everyone stay awake for the first hour. This contains some warm-up. We're going to talk about one-time truth tables, and then we're going to once again tell you about the beaver trick for evaluating circuits, and finally how to get active security using MECs. In the second part, I'm going to tell you about how to extend oblivious transfer against malicious adversaries. This is also quite cool, and this is also something that's in this paper. Or at least it's kind of hidden in this paper, but it's probably the main technical contribution was in this paper, which is an active security extension protocol, which only requires a constant number of, it only has a constant overhead on top of the passive OT extension protocols that you have seen on the other days. And Yehuda promised you that I'm going to explain how this works, so I'm going to tell you something about oblivious transfer properties and recap how the passive security extension works, and finally how our active secure OT extension works. In the third part, this is the one that is a little bit more messy, is where we're going to use this active secure OT extension, these OTs which are secure against active adversaries, to produce some multiplication triples which can then be used to perform secure computation using the protocol which we present in part 1. We'll talk about that later. So here there are some tricks about how to do authenticated local products, authenticated cross products, and Lego bucketing. So many of the choices, presentation choices in the next 3 hours are quite different from the ones that are in the paper. I think Yehuda told me at some point that this paper was really badly written, and he was very upset about this. And now I'm here, and since the paper is so badly written, Yehuda invited me to speak about this. So if you want to be invited to be to a winter school in the future, just make sure to write your paper. It's bad enough that Yehuda cannot understand them, so he will have to invite you to. All right. So let's start with the beginning. Once again, what is secure computation? So secure computation is this funny area of research in cryptography, where we have where we run protocols between Alice and Bob, where Alice has an input X, Bob has an input Y. They do some gibberish things. They exchange some cryptographic messages. They do something that looks gibberish. At the end, Alice learns the output of the function f on input X and Y. And we would really like that this protocol, this cryptographic protocol, behaves in the same way as if we had this magic box to which parties simply can input their input X and Y and receive the output afterwards. So we're going to compare, as Abi also recalled yesterday, we're going to compare these protocols with this ideal setting where there is some magic box that computes function for us. And clearly the setting with the magic box is secure by definition, right? So there is no arrow that goes from the box to Bob, which means that Bob doesn't learn anything. And the only arrow that goes from the box to Alice contains Z, which is the output computed of XY, which means that clearly Alice doesn't learn anything else. Also, the box computes, inside the box it says f of xy, which means that the box actually computes the function that you want to compute. And you can make a list of these properties if you want, like privacy of inputs, correctness of output, and other things. But the way we prove security, which I'm not going to do so much today, is by comparing the execution of this protocol with this setting, with this magic box that computes function for us. So what kind of secure computation we are going to talk about today? So secure computation is a very generic word. What do we mean when we say secure? There are so many adjectives you can put in front of secure, so let me specify. So the first thing is that I'm going to talk only about dishonest majority. Well, this, I guess, is the focus of the school. There wasn't really anything about honest majority, but let me stress it again. So all of the protocols here will be secure, even if the adversary can corrupt up to n-1 participants. And I'm going to focus on the case of two parties where the adversary corrupts one. I'm going to talk about static corruptions. I'm only going to consider static corruption, which means that the adversary chooses which party to corrupt before the protocol starts, as opposed to adaptive adversaries, which might choose which party to corrupt based on the protocol transcript. This seems to be like a reasonable choice, especially when we talk about two-party protocols, because to some extent, if I'm running with you, I don't trust you, but I kind of trust myself. And if I don't trust myself, I'm really in trouble. So this is the way I justify to myself why it's fine to only focus on static security. The real answer is that adaptive security is so hard to get, which we don't want to, but yeah.
With erasures, you don't get free here?
Sorry?
With erasures, you don't get anyone here? You erase the offline phase.
That's probably correct, but yeah, okay. Fair enough. Okay, you could also, okay, some of these things, okay. Not all of it will be adaptive secure. So I'm going to also consider active corruptions, which means that the adversary can behave arbitrarily. They can do whatever they want. This is also known as malicious or Byzantine. So when I started my PhD in Denmark at Aarhus University, this was when the first sugar bid auction was being deployed. And the sugar bid auction worked, they use a protocol which is secure if a majority of the participants are honest, and and assuming only passive corruptions. Which I assume, there is something cultural into this. Like if you go to Denmark, I guess that making the assumption that the majority of the people are honest and everyone behaves nicely, it's kind of okay. But if you're Italian like I am, those are clearly not assumptions that you're willing to make, and that's why the focus of my research is on dishonest majority and malicious parties. Finally, since we are in the setting of dishonest majority, we are not going to have any guarantees of fairness nor termination, which means that the output, there is no guarantee that anyone will receive an output, and if the adversary might get the output before the honest parties and then decide that the honest parties don't receive output. And this is why the box that I presented before only had one arrow that goes to Alice. So we're only going to look at the case where only one party gets the output, because essentially this is the best we can do. Then of course you can do tricks. All of these protocols will allow you to get both parties to give output to both parties, but this is not. You cannot guarantee that this is going to happen. So are any of the words on this slide still mysterious to you? No, good. So once again, so the ideal setting for secure computation is this world where we have some trusted party. So there is this nice police guy here that everyone trusts. And so if Alice and Bob want to compute some function of their input x and y, what they can do is simply to go to this guy. This is the woman in Texas that Abby was talking about, right? Everyone goes to this woman in Texas. You give them your inputs, and this guy computes the output for you and gives out the output, right? So clearly, it's not desirable to have such a central trusted party, because this central trusted party can, learns the inputs of everyone, can compute any function they want, and they could go around, they could go out and sell your data to other companies. So this is clearly not a desirable setting. So for the first hour of the talk, we're going to focus on this slightly different model, which I'm going to call the trusted dealer model, where we're still going to use some trusted party, so that we still have this police guy, but the role of this trusted party is slightly different. So before the protocol starts, we have this trusted party which samples from some distribution, D, samples two samples, RA and RB. So those are two random samples from a distribution. They're correlated, clearly. They get sampled together, so they can be correlated. And now this trusted dealer gives half of this to Alice and half of this to Bob. And now Alice and Bob, using their inputs and these correlated samples, they can actually run a protocol and get some output. So first of all, I want to argue that this is an interesting model in itself. First of all, in the second and the third hour, we are going to replace this trusted dealer with cryptographic protocols. But I'm going to argue that this is already an interesting model in itself, because this trusted party will not learn your inputs. This is a trusted dealer which will not learn your inputs unless it colludes with one of the two, with the other party. So this already is something. You could think of this trusted party being implemented in some kind of self-destructing hardware that outputs these samples and then blows up or something. And most importantly, we know that it's impossible to do secure two-party computation without cryptographic assumptions. And instead, I'm going to show you that using this trusted dealer is going to allow us to have secure two-party computation protocols which are information theoretically secure. Now, I'm not extremely interested in information theoretic security in itself. You will still need to have like an SSL encryption on a TLS on the channel or something. But what is really great about information theoretic protocols is that they don't use any cryptography. And cryptography is expensive. So information theoretic protocols only use operations like XORs and field operations, which are order of magnitudes faster than exponentiations or other cryptographic operations. So this is great. And this is really what is going to be then in the second and the third hour, what we're really going to talk about is this pre-processing model. Most of the things I'm saying now are also an introduction to the talk that Ivan is going to give tomorrow. So what we're going to do in the second, third hour, and what Ivan is going to do also tomorrow, is that we're going to replace this trusted guy with a pre-processing protocol, something where Alice and Bob can compute this correlated randomness, RA and RB. And the nice thing about this is that this pre-processing phase is independent of the inputs of the parties. The fact that this is independent of the parties means that you can actually be a bit sloppier about the security requirements. If the protocol aborts, you can give out all your internal randomness. There is no problem for privacy. And typically, this pre-processing phase does not depend on the function that you want to compute. It's typically generic. It typically only depends on the size of the function you want to compute later. So this is the same as saying, we know that tomorrow we want to do a computation. So let's run this pre-processing phase during the night, where computation is cheaper and we were not using our computers anyway. Because this pre-processing phase is going to crucially rely on cryptographic technology. Clearly, since we know that two-party computation is impossible. Then what happens is that at the end of the pre-processing phase, Alice and Bob can simply send these samples to themselves in the future, or just remember them. And now we can use these protocols from the trusted, these protocols that we talk about in this first hour, these protocols with the trusted dealer. We can simply use them, combine them to this pre-processing phase and get a complete protocol without any trusted party. And now the nice thing about this online phase is that this online phase uses all information theoretic tools, which means that it's order of magnitude faster, which is nice. So think of the example of we have an election, or we know that we want to do an auction on something in a month from now. The sorority example. We know that on this day we'll have to do this sorority matching, and for some reason we really care that from when we give the inputs to the function to when we get the output, it goes at most a few seconds. We want to get the output immediately after we provide the inputs. It's very crucial. But we know that this computation is going to take place in the future. So we can just start preparing for this. And then, when the time comes, we get an output very fast. So this is our model. So let's start with some warm-up. So in this first part, now I'm going to let's forget about cryptography, about cryptographic tools for the first hour. Let's just think about having this trusted dealer guy that gives you this correlated randomness, and let's see what we can achieve in this model. So as a warm-up, I'm going to tell you about one-time truth tables, which are the simplest MPC protocol, two-party computation protocol which you can imagine. So if this is the third day of the school, if you're still unsure about how can we do secure computation, this is the chance for you. Like, I mean, if you don't get this, I guess I really like this So this is a really nice protocol, and I think it can also be. It's very easy also to teach in classes. At least my students find it easy to understand. And then we're gonna talk about circuits and then make and compute. But let's start with these one-time truth tables. So again, the simplest two-party computation protocol ever. The setting is we have a trusted dealer, Alice and Bob. The trusted dealer samples, these two samples are A and are B, gives them to Alice and Bob. Alice and Bob have some inputs now. They exchange some messages. At the end, they get the output. So let's see. What does this trusted dealer have to do? So the first thing that the trusted dealer needs to do is that it takes the function that Alice and Bob want to compute and writes it down. It writes down the truth table for this function. So here you have every column corresponds to an input of Bob, every row corresponds to an input of Alice, and in each box, I have to point that way, yeah? And in each cell, I put what the output of the function is on that particular input. So far, so good. The second thing that the trusted dealer does is that it picks two random indices, R and S, and simply uses them to rotate the columns and the rows of this table. So here there is a 3 here. You shift it 3 positions in that way, 1, 2, 3, and 1 down. The 3 gets here, and if you have the slide. So if you look at them, you can see that I'm just rotating the table by 2 random shifts. So far, so good. Finally, the trusted dealer gets samples a random matrix, T1, and computes T2 as the permuted truth table minus this random matrix T1. So this is simply an additive secret sharing. So one note about the notation in the slides, every time you see a plus or a minus, those are plus or minuses in a group. And for whatever group, those are like, in most cases, those would be like addition modulo something, or XORs. The modulo is always implicit, but so don't get, those are never, plus and minuses are never integer operations, are always group operations. So the police guy simply perform an additive secret sharing of this truth table, and now there are these two shares. So now the trusted guy gives T1 to Alice, together with the shift of the rows R, and T2 to Bob, together with the shift for the column S. Now Alice and Bob finally get their inputs, X and Y, and what they do is the only thing they can do. They exchange one-time paired encryption of their inputs. So Alice sends X plus R to Bob. We call this U. And Bob sends Y plus S to V, to Alice. We call this V. Right? Bob also sends the entry of his matrix in position UV. And now Alice concludes that the output of the function is T1, so her own table in position UV, plus T2 in position UV. It is a simple protocol. It fits on one slide. It's the first two-party computation protocol you've ever seen that fits on one slide, and there is still space. So is this protocol correct? Is the actual output we wanted to compute? Yes, by construction. Just go back to one slide and see that T1 UV plus T2 UV was defined as the function, as the truth table in position X minus R and X minus S. I'm not going to ask you to do it now, but you can easily verify this. So this is the right output. So this protocol produced the right output. Is this protocol secure? Well, the only thing we're exchanging are like essentially one-time paired encryptions of the inputs. So nothing is wrong, right? In particular, if you look at the first message, the first message is X plus R, but R is a uniformly random element in Bob's view. So Bob doesn't learn any information about X from this message. And Alice only sees V, which is Y plus S, but S is uniformly random in Alice's view, so she doesn't learn anything about Y. Of course, Alice also learns this value, T2 UV, but this is just a random share, conditioned to the probability, conditioned to the fact that tu uv minus plus f of xy is equal to this value, which essentially means that you can simulate this, right? So I mean, this is a value that Alice can compute from the randomness she gets from the trusted dealer and from the output she's supposed to get in the computation. So this is not giving any extra information. That's great. So are we done? Can anyone come up with some reason why this protocol is not secure? Sorry? Man in the middle? No, there are only 2 people in the world. Alice and Bob are alone in a room, and there are no other people in the room. Yeah? The V that he sends is not the right V. So Bob could lie about the message V he sends. That's true. Any other attack?
T2.
Sorry? T2. So we have so Bob could lie about the share V, and Bob could lie about this share TU. So let's see what happens. So let's see what happens if Bob is a pirate. So like you said, if Bob is a pirate, Bob can add some error. So instead of sending V computed as y plus s, he can compute this as y plus s plus E1. And instead of sending T2, he can send T2 UV plus E2. Can add some error to his messages. So is this really cheating? So let's look at the first message. So if Bob computes V like y plus s plus E1, like someone said, is this cheating? This is actually not really cheating, because you can just reorder, this addition, and this is you can just put the error in here and just say that y plus E1 is y prime, and this is the actual input that Bob is using. Now, since we allow active adversaries to change their inputs in the ideal world, this is not an attack to the protocol. So this essentially means simply that Bob had a different input. So there is no way of cheating in the first message. However, the second cheating, M2 plus C2, this is actually a real cheating. Because this changes the distribution of the output. This makes the output be Z prime, which is f of x, instead of being f of xy, is f of xy plus E2. This is actually a problem. Why? Think just let's just make, just for the sake of the argument, assume that Alice and Bob were computing the function that outputs 0 on all inputs. Of course, they were not computing this stupid function. But let's suppose that they were computing a function that outputs 0 on all inputs. Then, of course, if E2 is equal 1, this makes the output of the function being 1, which is clearly something that could not have happened in the ideal world. In the ideal world, the output of Alice was always 0. Now, in the protocol, Bob can make Alice output 1. So this is a breach of correctness. So this is a problem. And how are we going to solve this problem? We have to force Bob to send the right value. And how do we force Bob to send the right value? We use message authentication codes. And we are lucky enough that we can use message authentication codes, which are information theoretic, since we only have to use them once. So in particular, the following here, it's a very nice information theoretic message authentication code. The key is A, B, which are just 2 field elements. F is some field here. So you sample A and B, and then you compute the MAC of some entry T as A times T plus B. So now what happens is that the trusted dealer gives Alice a key for this MAC, A comma B, and Bob is shared T, but he also has this MAC M. And when Bob wants to send his share, he must send the MAC together with his share. And it's easy to see that, and of course Alice will check if the MAC is valid, and if the MAC is not valid, she will abort. It's easy to see that if Bob can send 2 different MACs that make Alice not output abort. So if Bob can send a MAC that make Alice output the wrong value, that means that he has 2 MACs for 2 different values T's, which means that you can just solve a system of 2 equations and you can recover A and B, but if the field is big enough, this is never going to happen. So this is really, I'm going to keep using MACs of this form for the next 3 hours, so this is the time to ask a question. Yeah?
Do you need it for every element in your T1?
I will need it for every element. Are you all persuaded that this is a good way of making sure that Bob doesn't lie? This is really what we're going to keep using for the rest of the day and tomorrow. So let's now see, let's create a protocol which is secure against a corrupted Bob. So the protocol is the same as before. But now together with these tables, the trusted dealer gives Alice a matrix of, this is Mutu's question. We need to have a MAC key for each entry in the table. So for each entry in the table, we have a MAC key A and B. And Bob gets a MAC M. And now Bob sends together with this share also this MAC in position UB. And of course, Alice, instead of outputting f of x, the first thing she does is she checks that this is a correct MAC. And if it is, she outputs the value. Otherwise, she aborts. Yeah? Because they are like, if you have two MACs with the same key, then you can recover the key. Because the key, the MAC is simply, yeah. I want to have information theoretic security. So Vadim's question was, can we use signatures? Of course we could use signatures, but we want to have information theoretic security. In this, we don't believe in cryptography for the first hour. Yeah.
So this MAC is on T2, right?
Yeah.
It doesn't matter if it was on T.
So I'm adding MACs on the individual on each share on T2.
No, I mean, would it matter if it was on T, so T1 plus?
So that's a very good. So the question is, why do you add a MAC on the share? What you really care about the correctness of the output, not about the correctness of this share. So why do you put the MAC on the share and not on the output? This is a very good observation, which will be used by Ivan tomorrow. Great. So this is the simplest protocol you can imagine for two-party computation with active security. Actually, this is not completely true. OK, so is this secure? Yes. This has statistical security if even against a malicious Bob with probability 1 minus 1 over f, which is the size of the field. Why? Because, of course, Bob could guess the key of the MAC and then could forge every MAC, right? So the probability that he guesses this A right is 1 over f. So this is almost the simplest protocol that you can think of for active security. You can actually get a protocol which has perfect security. And once again, it's not because you necessarily need to care about perfect security, but the nice thing about perfect security is that if you don't have any security parameter, then the protocol must be simpler. It cannot depend on any security parameter, right? This protocol depends on the security parameter. It means that this MAC has to be of size at least log of size of f, right? But if you have a perfectly secure protocol, then you don't have any security parameter, then the complexity of the protocol cannot depend on the security parameter. So it's just more efficient. So this is a different way of thinking about why you should care about more secure protocols. And if you want to have perfect security, actually we can do this. And these protocols that I presented before, this one-time truth table, together with this perfect secure version, is in this paper that I wrote with Yuval and Eyal and Sigurd and Anat, which appeared at TCC 2013. Yeah?
But what about if I limit the amount of information that you can do in the trust interface, then what happens?
That's a very good question, which I don't know the answer to. The question was, what can I limit the amount of the information that needs to be sent in the online phase?
Independent of the function, that's all.
Right. So this leads to naturally to the next slide, which is, this protocol is great, it's simple, it fits on one slide. It has even optimal communication complexity. All the parties only have to exchange a one-time pad encryption of their inputs, which is together with a share of the output, which is kind of optimal for at least if you want a protocol that works for all functions. But of course, there is a huge drawback, that is the storage complexity for the parties is exponential. You need to store the whole truth table, right? The preprocessing phase contains the whole truth table of the function. So if you want to do a function, if you want to evaluate a function where the input have come from a big domain, this is completely impossible to do. So of course, what we're going to do is that we're going to represent the function using circuits instead of truth tables. And this is where we're going to go back to Beaver trick. So first of all, let's agree on what circuit-based computation is. So we have Alice and we have Bob. Alice has some input x1 to x5. Bob has some input y1 to y5. They are inputs to some booleans, to some circuits. The circuit contains multiplication gates and addition gates in some field, or and I work very hard to make this a circuit and not a formula. As you can see, there is fan out is allowed. So this gate has fan out to both of these gates, also this. Don't write, don't talk about circuits and then have formulas on your slides. That's bad style. And at the end, Alice gets the output. So I'm going to give this protocol. I'm going to tell you how to evaluate input gates. So how to give inputs to the circuit, how to compute addition gates, how to compute multiplication gates, how to compute output gates. So for each of these 4 kind of gates, input, output, addition, and multiplication, I'm going to tell you how to do this. And then the overall protocol is simply that you take the circuit, you start from the input gates, you evaluate those, and then you go down the circuits and you evaluate all the circuits, all the gates as soon as all the inputs are ready, and then you get the output. So I'm just going to tell you about how to evaluate these 4 kind of gates, and then you should be able to evaluate any circuit you want. So we're going to use this invariant, which is that for each wire x in the circuit, we're going to write x in a box. So x in a box simply means that the value on the wire x is secret shared between Alice and Bob. So Alice has a share xa, and Bob has a share xb. If you sum them together, it gives x. So this is simply the invariant. X in a box means an additive secret sharing of x between Alice and Bob. And I apologize for this kind of notation overload. There is a note here which, sometimes when I write this x here is a value, right? This is a 0 or 1. This x here is the name of the value, but I hope that the confusion is not too big for you. Read the footnote if you're confused. So how do we do input gates? Input gates are easy. So if Alice wants to input a value x to the circuit, what she does is simply she chooses a random share for Bob, xb. She sets her own share to be x plus b. Minus b would be better. Yeah, correct the slide, minus b. X minus b. Because we want that xa plus xb is equal to x, right? So Alice sets xa to be x minus xb. And then sends the xb part to Bob. This is clearly secure, right? I just sample a random value and I send it to you. Who cares what I do in the private of my own home? Well, who cares what I do with xa? I just send you a random value, so this is clearly secure, at least if you think about passive adversaries for now. How do we open a value? How do we evaluate an output gate? Again, it's easy. So I'm going to use the notation, this notation. So you have you open z in a box and give it the result to a. So Bob has a share for z. Bob simply sends his share to Alice, and Alice reconstructs the output, right? Is this secure? Of course. Alice was supposed to learn z anyway, so of course this is secure. Or, if you want to be more formal, you can simulate this. How do you do addition gate? Yeah?
What against Alice Bob?
We are going to go. See, now Bob is nice. He's not a pirate yet. But very good point. So how do we evaluate addition gates? So we have x in a box and y in a box, and we want at the end to get z in a box. Z in a box should be x plus y. So this is very easy because Alice has xa and ya, and Bob has xb and yb. And since this secret sharing is additive, if you just sum your shares, then the share you get are a secret sharing of the output you wanted, right? So if Alice computes za equal xa plus ya and Bob computes zb equal xb plus yb, the output za plus zb is equal to x plus y, right? And there is no interaction, so clearly this is secure. So what is okay, so just to be like overly verbose and to be completely, to make sure that I define everything, you can also evaluate gates which are, how do you evaluate a multiplication gate by a constant? So you have a secret value x in a box, and you want to multiply it by a public value a, which is known by both Alice and Bob. How do you do it? Well, simply both parties multiply their share with this, right? Because the secret sharing is linear, the sum works. And how do you add a constant value to a secret value? Well, this is actually the only one that is not symmetric. So because if you add a 2 times, then you get 2a, right? So if you want to add a public value a to a secret value z, to have a secret value x, you simply add, Alice adds this public value a to x, and Bob does nothing. Again, of course, this is secure. We didn't even talk to it. No communication was performed. So of course, this is secure. So now let's get to the meat. So how do we do multiplication? How do you compute z as the product of x times y if starting from 2 secret sharings of x and y? So if you have x in a box and y in a box, how do you compute x times y in a box? So what we want to do is that Alice and Bob want to compute this za plus zb, which is xa plus xb times ya plus yb. Now all the red values are for Alice and all the blue values are for Bob. Which if you expand this, it gives you this very nice expression. And there is not this magic about this. This is actually very simple math that, don't trust Yehuda. This is very simple math. Everyone can do it. And if you look at this, this is easy. So there are 2 parts of this that are kind of easy. So xa times ya. Alice has both of these values. So Alice can compute this part of the product on her own. And Bob can compute this part of the product on his own. But what about this stuff in the middle? So this stuff in the middle has 1 share of Alice together with 1 share of Bob. How do we multiply something that I have with something that you have? So how do we do this? Anyone has any guess? So I mean, if x and y were coming from a small domain, if you're working on a small field, you could simply use the one-time truth table protocol that I presented before, right? That allows you to compute any function. So in particular, you can also compute this function. But there is a much better way of doing this, which is this Bivet trick, which goes as follows. So if you want to multiply x and y in a box, the first thing you do is that you get a random multiplication triple from the trusted dealer. So finally, we use the trusted dealer. You go to the trusted dealer and say, hey, can we please get a random multiplication from you? The trusted dealer gives you a in a box, b in a box, and c in a box, such that c is the product of a times b. And now what you do is that the first thing you do is that Alice and Bob together open these 2 values, a plus x and b plus y, call the results a and d. This is of course secure because a is random, b is random, so e and d are one-time paired encryption of x and y. And what you do is that you compute this very nice expression down here, which is simply a linear combination now of things that I told you how to compute. So this c is this c that you get from the random dealer, from the trusted dealer. E times y, this e is this public value that is here, and I told you how to compute multiplication of public values times values in a box. Same thing for d times x. And minus ed, e and d are 2 public values, so both Alice and Bob can just multiply them in the clear, and I told you how to do additions of public values to secret value. And now if you expand this, you know that c is equal to a times b. E times y is e times b plus e times y. No. E times y is a times y plus x times y. Plus bx plus xy. OK, it's a little bit magic. And then minus this last part here. And I color-coded this in here so that you can see that this AB goes away with this AB, this AY goes away with this AY, this BX goes away with this BX, this XY goes away with this XY, and all you're left with is this X times Y, which is exactly what you wanted to compute. So once again, this is simple and everyone should know it. So if you don't, do. And as I tried to say already, this is secure because E and D are simply to one-time paired encryption of X and Y using A and B. Yeah?
It works in higher fields as well.
It works in any field, yeah. So actually, yeah, so Mutu's question was for which fields does this work? This works for any field. That's why I wrote minus. If you want the, if you only care about the Boolean version, then minus and plus are the same thing. So the formula is even simpler. Great. So there was a good question before. What do we do against corrupted Bobs? So what do we want to do when Bob is corrupted? So when Bob is corrupted, we have two problems, right? One problem, I mean, at least there are two things that could go wrong. One thing that could go wrong is that Bob learns some of the internal values, so learns some of the values on the internal wires. This is bad, right? Bob should not learn anything. He should not learn, so in particular, he should not learn any value on any wire. And also something that can go wrong is that, it could be that Bob can add some error to some wires. This would also be bad because that would lead to an incorrect result. So we need to worry about these two kind of attacks. If you think long enough about the protocol I presented before, you should realize that even a malicious Bob cannot do anything to learn anything about the values on the wires. All the operations we did were, so the only information Bob got was random shares from Alice during input gates and opening during multiplication gates of random values. So Bob doesn't learn anything. Even if he's malicious, he's still not going to learn anything. But of course, correctness is a big problem because a corrupted Bob can change his share during any of the opening phases, and which would result in, which is the same as adding errors to any wire. So let's look at it again. So when you do an open, so the protocol says that Bob should send his share ZB to Alice, and then Alice should output the sum of the two. Of course, if Bob is corrupted, he can add some error here, which would propagate to the output that Alice outputs, which is of course really bad. So how do we fix this? We use mechs. I only know two tricks, so this lecture is going to be very repetitive. I'm always going to use the same two tricks over and over again. So the solution is that we are going to enhance the representation of X. So from now on, instead, when I write X in a box, I mean something a little bit more complicated than the thing I wrote before. So the new X in a box contains 3 values for Alice and 3 values for Bob. The first value is the secret sharing of X, like before, XA and XB. The second value is a key, and the third value is a mech. So both Alice and Bob have a key and have a mech. How are these values all interleaved together? So the mech that Bob gets, MB, particular to this value X, is computed as like before, AX plus B. In this case, A is called delta because I want to call it delta, and B is called K because I want to call it K. But it's the same. So the mech is still exactly of the same form as before. You have some key, which is composed of 2 elements, delta and Ka, delta A and Ka, which you use to compute a mech on XB. So this means that Bob has a mech on his own value under the key of Alice, right? This of course makes sense. I have a mech on the value I have under the key that you have. And the same thing goes symmetric for Alice. So both parties have a mech on their share under the key that the other party has. So what is this value delta? Why did I write it here, not there? Because we're going to use a constant value delta for all the wires of the circuit. So this K value is going to be local to each wire. Each wire has a different K. But this delta is going to be the global over all the wires in the circuit. So now, if you're paranoid, you might worry, is this mech still secure? Before I argued that if you have this mech with one key, it was secure. Now I have this. Now I give you a lot of mechs on a lot of different values under keys that are related. All the keys share the same delta. So is this still secure? Is this still secure? So how many equations do I give you? I give you as many equations as the number of values you get, right? So you have one equation for each wire. So each mech defines one equation, right? So you have one equation for each wire. And how many unknowns are there? You have one, for each wire I have one unknown, Ka. And then there is one extra unknown, which is this delta, which means that you still cannot guess the key, right? There is still 1 degree of freedom. You can't just solve this, you can't just solve the system. There is still something that you cannot guess. So the security of all of this will really boil down to saying that Bob cannot guess this delta. So how do we open now? So Bob, together with sending his value ZB, is also going to send the mech, MB. And what does Alice output? She checks if the mech is correct. And if the mech is correct, she outputs Z equal to ZA plus ZB. And if the mech is incorrect, she aborts. You have a question? You look like someone that has a question. No? Okay. So again, this is, these max are really the trick that we're going to use over and over again. So, yeah.
The deltas are shared also, like before their system parameter?
Yeah, so deltas are system parameters. They're not shared. So Alice knows delta A, and Bob knows delta B, and it's only one value for the whole circuit. So the K part of the key is local to the wire. The delta is global to the circuit.
But it needs to be considered the preprocessing phase.
Say again?
You need to know delta the preprocessing.
So the question is where all this stuff comes from. So all this stuff comes from the trusted dealer at this stage, right? There is this trusted dealer. He's so nice. He keeps giving us correlated randomness. If we can ask him for random multiplication, we can also ask him for random multiplication together with the max on the multiplication side. It's nice. He doesn't care to do a little bit more computation for us. Right. So why am I setting this delta to be the same? I told you still secure, but why is this a good idea? It is a very good idea because, of course, now we know. I mean, the opening phase is secure, but we don't want to lose the ability of computing on this representation. And to be able to compute on this representation, we want this representation to still be linear. What do I mean by linear? I mean that given x and y in a box, I want to be able to compute x plus y in a box, right? So how do you compute x plus y in a box from x and y? I simply, the representation is completely linear. So Alice simply adds all the parts of her representation. Bob simply adds all the parts of his representation. And since the representation is linear, this works. So let's do it once. So let's look at the Mac that Bob gets on this x plus y. So this is the Mac on, this should be an x here. So typo, correct this typo. This is x, mbx plus mby. But what is this? So mbx is the Mac on x, which is of this form, plus the Mac on y, which is on this form. And now you see why it's important that delta is a constant, because the fact that delta is a constant means that I can take delta out of this, and I can write x plus xb plus yb times delta, which means that this is the Mac of the right form, right? So it's crucial that we have this part of the key is global to the circuit. This allows you to still be able to compute, to do linear computation on these values, which means that everything I told you before, for the passive secure protocol, you can keep doing. Just replace, instead of using the class secure x in a box, passive secure x in a box, now you use the class active secure x in a box, and you still write additions, and this all works. So let's do a little recap of the protocol. So we have the trusted dealer at the beginning. It gives you random multiplications together with these max. How do you compute output gates? To evaluate output gates, you exchange shares together with max. And if the max don't verify, of course you abort. Why would you have max anyway? How do you compute input gates? This is a bit different. So what you do is that you get a random R from the trusted dealer, R in a box. And you open it. You let Alice learn this value R. And then Alice sends to Bob the difference between this value R and X. And then what you do is that you compute a secret sharing of X in a box, by adding R plus T. So this clearly works, but why is it needed? We wanted to extract the inputs. So in the first protocol, in the one-time truth table protocol, we realized that when Bob cheated in the first message, this was not really cheating. It was the same as using a different input. What does it mean that it's the same as using a different input? It means that Bob knows which input he's using. Why does Bob know which input he's using? Because the input he's using is defined by the difference between the message he sends and the randomness he gets from the trusted dealer, right? He knows which message he sends. He knows which message he gets from the trusted dealer. So he can his input is well defined as the difference between these two values. And this is what we do here. We simply have a way of saying, now we know that Alice knows what her input is because she knows what she gets from the trusted dealer. She knows what she sends to Bob. The difference is her input. Addition gates are easy. Just use the fact that the representation is linear and do this. And multiplication is like before. Get a random triple ABC for this new augmented representation. open END, compute this linear operation, and now since all these operations are now these opens are not the old opens. Those are the opens where you check the max, right, before outputting. And these pluses here are not the pluses. These are the pluses where you also add the max and the keys. Now this makes the whole protocol secure. Okay, so this is the complete protocol, which is nice because it allows you to compute any circuit, arithmetic circuit, with information theoretic security, assuming a trusted dealer. Also against active adversaries. Yeah?
Just to check on the missing thing. So it's actually just a single map on every input bit, and then you use the same just homomorphic operations on those max the whole way through the circuit. You don't need to add any additional.
So the question is, how many max do I need? So you need, so for each input gate, you need one random value with a mac. And for each multiplication gate, you need a multiplication triple. And each multiplication triple contains max as well, right? So if you have, so the number of shares, the number of objects you need to ask from the trusted dealer is one random value for each input gate and one random triple for each multiplication gate. And each of these guys contains max and keys, all using this global delta. Yeah?
What about selective failures if I swap one particular bit and assume that he avoids if like multiplication is 0 or is is 0 or not?
So that's a very good question. The question is, what happens with, are there any selective failure attacks? Which means, can we make sure that the protocol aborts? Can Bob do something such that the protocol aborts if one input is 0 or 1? No, no. So when you send a MAC, you either send the right MAC or the wrong MAC. The MAC does not depend. If you can, okay. So let's put it different. So if you could send a MAC that only works for one of the two values, I could extract a key from you. You can just, because you know a MAC on the right value. So if you get the MAC that works only on one of the two values, then I can extract a key from you. So no selective failure attacks. This is, secure, simple, everything you wish for. There are a couple of problems. So there are two things that you can do to do this protocol better. So I think, again, so this is something simple that I think you can explain to anyone. This is just how to evaluate circuits with active security. There are two things that you can improve. One is the size of max, and the other one is the communication complexity. So the first thing about the size of max. So how big is this representation X in a box? So X in a box means that if you are two parties, Alice has a MAC on the share of Bob, and Bob has a MAC on the share of Alice. If you're 3, you need to have a MAC on the share of everyone else. If you're 4, so the number of the size of this representation, the size of X in a box, grows quadratically with the number of participants, which I don't care when I have only 2 parties, but it's a problem if you want to have more than 2 parties. And Ivan tomorrow is going to tell you about speeds, which is something which is a not different protocol, which has where the size of this representation is linear in the number of parties. The price to pay is that the online complexity now must use some kind of cryptographic operation, but not so much. So it's still good. But if you're a purist of information theoretic security, you must, you can't use that. Yeah.
Lower bound, you think there exists a lower bound, or we don't?
So okay, the way it's in. So okay, no, that's so you can do it. You can do it also information theoretically, but then the size of the max, then you need to have bigger max, right?
No, I mean, the point is that you don't really need any computation assumptions for that. There's implementations.
Yeah.
Assumptions for efficient consent.
Yeah, okay.
You can do this.
Can you repeat? I didn't.
So Ivan says that the implementation of speeds uses computation assumptions to make the online phase more efficient. But if you want to insist on having the online phase information theoretic, you can.
that's going to be asymptotically what you say.
which is going to be, but then it's going to be asymptotically linear, but not amazing in practice. Okay, let's take this to multiply. So the second part is, of course, that the MAC, these MACs are only as secure as as it is hard to guess the key. So if you're working on Boolean circuits, for instance, and you're doing MACs with bits, these are clearly not very secure MACs, because if the key is 1 bit, then with probability 50% that adversary can guess the right MAC, right? So the solution is simply to have a lot of MACs in parallel. So if you are working with bits, instead of having the MAC being 1 bit, you just have like you just have a vector of MACs, so a bit string, and the key is not 1 bit, but it's a vector of bits, a bit string. But if you're working already in a big field, then this is fine, right? Yeah.
So all of these max have different keys and delta.
So repeat.
The delta is different for all these k-max, or is the same?
The delta is different. Yeah. So those are like k parallel max, which different deltas. Which means that in TinyOT, which is the protocol I'm going to talk about today, the max and the keys are k-bit strings, because bits are not good enough. If you want to insist on having max, which are on having representation which only grows, which only has a constant overhead for active security, then you need to use this other protocol which is called minimax, which Ivan is going to talk about tomorrow.
The error that using bits, so it's 2 to the minus k, it's that's for a single map, or is that because you have maxing all the circuits, you actually get the size of the circuit over 2 to the k, or you don't?
No, you don't. You don't, because if you send a wrong MAC, then you get then aborts, right?
You're adding things together.
So the analysis doesn't need a union bound over the circuit size?
That's what I'm asking, because you're adding things together.
So that's the second part, which we actually, that's what actually we do. But no. No. The other part was this problem of having of a malicious bulb which can add errors to the wires of the circuit, right? And here the observation we do is that it's a problem if the final output is incorrect. So what happens if Bob adds an error on any of these wires? The output is going to be incorrect, which is of course a problem, right? So if the final output is incorrect, it's of course a problem. But do we really care if any of the values on the internal wires are incorrect? Not so much, because those values are never open. I mean, Alice never learns these values, right? So as long as the final output is correct, we don't really care about if the internal wires are not correct. Which means that we can do this other trick, which is this idea of doing lazy MAC checks, which means that every time we evaluate a multiplication gate, we don't need to send the MACs together with the shares. So every time we evaluate a multiplication gate, instead of using the open function that I defined before, we use the different function, which is called partial open. A partial opening of a value z in a box says that Bob should send his share to Alice. That's it. He doesn't send anything else. But Bob remembers which MAC he should have sent. So let's say that there is some, he has some list out MAC to which he appends the MAC he should have sent. So Bob remembers which MAC he should have sent. Alice, she remembers which MAC she should have received, which she can compute now because she knows she knows the key, she knows delta, and she knows ZB because Bob just sent it to her. So Bob remembers the MAC. Alice remembers the MAC which she should have got. Alice says, okay, let's hope that everything is all right. Let's just output this value Z. Who cares? And then when you do a final open, when you're actually opening the output of the circuit, you start by doing the same thing as before. And now you check that the two MACs that all the MACs that you should have sent me are the same as all the MACs that you actually sent me. All the MACs that you should have, that these two long strings are the same. And this, you can do this if you believe in the random oracle. Bob can simply send can send a hash of all this long string to Alice, and now she can just check that these two strings are the same, right?
Collision resistant hash wise maximum.
I think we need to extract them also at some point.
So can you repeat why do you need to do that? Why can't you just check through computation?
So this is because we want to reduce the communication complexity. So so let's analyze the communication complexity of this protocol now. In the previous protocol, in every multiplication gate, I had to send you a KB string. Now I only send you one single KB string at the end of the protocol, which means that the communication complexity now is the size of the circuit plus security parameter, instead of size of the circuit times security parameter. Which means that you can go down from 100 times the circuit size to circuit size plus 100. Yeah, you're right. Collision resistant is fine, probably. Yeah.
Just on the input wires.
Yeah. And if the Mac is wrong, you abort. So how am I doing with time? Do I have 50 minutes more, or should I stop still at 11? 5 minutes more. Okay, 5 minutes more. So this is the end of part 1. What did we learn in part 1? In part 1, we've seen two protocols in the trusted dealer model. We used almost no cryptography. Only at the end I used this hash function. Otherwise, this was all things that you can teach to someone that goes in high school, because it only uses addition and multiplication. We have these two protocols, the one-time truth table protocol, which is bad because it uses exponential storage in the input size, which means you cannot use it for function with big inputs. But if you want to securely evaluate some function on small inputs, 8 bits, 10 bits, why not? The communication is very good, and it only takes one round. And then you have these other kind of protocols, this securely evaluating the circuit gate by gate, which is, and what I presented is essentially the online phase of this paper called Bedoza and TinyOT, where the storage complexity for the parties, so the amount of data they need to receive from the trusted dealer, is linear in the number of the AND gates and input gates. So for each AND gate, you need to have, every time you have a multiplication gate, you need to ask the trusted dealer for a triple. The communication is linear in the number of the multiplication gates. So for each multiplication gate, you need to exchange some messages. And the number of rounds of this protocol is the depth of the circuit. Why? Because every time you have a multiplication gate, you need to do an opening, right? So every time, of course, you can layer your circuits. You can look at your circuits in layers, and then parallelize all the openings for one layer of ends at the same time, right? But still, every time you have a multiplication, you need to do an open before you can continue the computation. And someone yesterday asked me, why do we care about the round complexity of protocols? It depends, right? If you're running a protocol between someone on Earth and someone on Mars, then the random complexity of the protocol is really bad, because the time it takes to send messages from one end to the other it takes time, and every time you have to wait for the message to arrive. But if you're running a protocol on two machines that are connected with a huge cable like the one that Abby has, maybe it's not so much of a problem. So it depends. So great, we have these two protocols. And if you want to get active security, what you do is simply you add enough megs to any of these protocols, and you get active security. So this is the recipe for protocols in the trusted dealer model. So the final words on this part 1: to do secure computation, the take-home message is that to do secure computation is enough to pre-compute enough random multiplications. So just ask your favorite trusted dealer for a lot of multiplications, or compute them yourself at night, and then you'll be able to compute any circuit you want. And in the next 2 hours, we're going to replace the trusted dealer with cryptographic assumption. In particular, from now on, we're only going to focus on Boolean circuits, and therefore our cryptographic assumption is going to be oblivious transfer. And then that's what we're going to do now. So